Welcome back. In this video, we'll shift gears a little bit from transformations to talk about moment generating functions. So we'll start by defining a moment generating function, what this thing really is, what it does. We'll talk about some properties of moment generating functions and why these can be incredibly useful to us. And then we'll provide some common moment generating functions. So let's start by explaining why we need a moment generating function, why these things are useful. Well, it turns out that the parameters of a distribution, like the population mean, mu, the population variance, sigma squared, describe the center, describe the variability of a distribution, but they're not unique. We can have multiple distributions with the same expected value and the same variance. So on their own, they don't provide enough information to tell us everything we need to know about the distribution. However, we can define a distribution uniquely using its moments. So let's talk about what a moment represents. So the kth moment of a random variable is defined as the expected value of y raised to the k power, which we'll denote as mu with a prime k, so mu prime k. These moments themselves are unique. So not just the first moment, which is the mean, not just the second moment, which is the expected value of y squared, but if we have all of the moments of a distribution, that is itself unique. Now, the moment generating function is a shortcut, if you will, that we can use to provide or find all of these moments. And the moment generating function is defined in the following way. We say that the moment generating function m of t is the expected value of e raised to the t y power. So this is not a function of the random variable y itself, this is a function of t. Now, why do we call this a moment generating function? Well, it turns out that with a little bit of manipulation, we can use this function to help us find all of the moments of a distribution. Now, this moment generating function, or MGF of y, exists if there's a positive constant b such that the moment generating function is finite, where the absolute value of t is less than this constant. And it turns out that for practical reasons, we'll really only be considered t in small neighborhoods around 0. So why is this the moment generating function? Well, it turns out that has to do with the Taylor series. So let's start by just refreshing our memories on what this Taylor series actually is. The Taylor series is a way to expand the e raised to the x power. So it turns out that e to the x is defined as the sum from n equals 0 to infinity of x raised to the n over n factorial. So we can write e to the x as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So let's apply that to the moment generating function. The moment generating function is the expected value of e to the ty. What does that e to the ty look like in terms of the Taylor series? Well, it looks like this. It's the moment it's the expected value of 1 plus t times y plus t times y squared over 2 factorial plus t times y quantity cubed over 3 factorial, and so on. So that's what the moment generating function is calculating for us. Now, if we distribute that expected value through, we get something that looks like this. We have 1 plus t times the expected value of y plus t squared times the expected value of y squared plus t3 times the expected value of y cubed. So there are the moments baked into this function. Now, how do we get the moments of a distribution back out? Well, we'll do that by taking derivatives. We'll take derivatives with respect to t. So let's take the first derivative with respect to t of the moment generating function, and we get something that looks like this. We get 0 plus the expected value of y plus 2t over 2 factorial times the expected value of y squared plus 3t over 3 factorial times the expected value of y cubed. Now, look what happens if I plug in 0 for t. Well, if I plug in 0 for t, expected value of y squared goes away, expected value of y cubed goes away, and so on and so on. The only term that is remaining is the expected value of y. Now, let's do this again. So let's take the second derivative. So second derivative with respect to t, this first 0 term will remain 0. Derivative with respect to t of the expected value of y is 0, and so on. So we get something that looks kind of like this. Take this second derivative, evaluate it at 0. What do we get? We get the expected value of y squared, and so on. So to get the kth moment, find the kth derivative of the moment generating function and evaluate it at 0. This will work as long as the moment generating function exists, so we can continue to do this for any positive integer k. So we'll do that to get the moments. So let's find the moment generating function of some distributions. First, of the Poisson distribution. So the Poisson distribution is a discrete random variable. It has count values, so y takes on values of 0, 1, 2, 3, etc. The probability mass function of y is lambda raised to the y times e raised to the negative lambda over y factorial. So to find the moment generating function, what we need to do is find the expected value of e raised to the ty power. So we'll take the sum, because of this is discrete, as y goes from 0 to infinity of e raised to the ty times lambda to the y, e to the negative lambda over y factorial. Okay, that's going to be a lot. We'll combine some terms together to see if we can make this a little bit simpler. So we get lambda e to the t raised to the y times e to the negative lambda over y factorial. We're going to use a tried and true strategy here. The strategy that we're going to use is to try to make this look like a PDF. So I'm going to try to rearrange everything in the summation to get another PDF, specifically another Poisson PDF. If I can get another Poisson probability mass function, that should sum to 1. So that's why we want to take this step. In order to do this, I like to pull any terms that aren't going to be in that PDF that I'm looking for, or that PMF that I'm looking for, directly to the front. So here, that's why we have pulled this e to the negative lambda out of the summation, because it's not going to be in the PMF that we'll try to collapse down to 1. So here we go. We will multiply by e to the lambda et. We'll divide by e to the lambda et, so multiply by e to the negative power. The reason that we will do that is because this summation term here now looks like a Poisson. It's a Poisson where lambda, or the lambda parameter, is actually lambda times e to the t. So that sum becomes 1. That means that our expected value of e to the ty, or our moment generating function, is e to the negative lambda times e to the lambda et. We'll simplify that just a little bit, and we get this. Our moment generating function for a Poisson is the expected value, is the exponential of the quantity lambda times e to the t minus 1. Anytime it gets to be a little bit too much in that exponent or in that e term, I'll shift to writing this as exp, just so we don't have too much little in the exponent. Now let's find the moment generating function of the exponential to get a bit more practice. And as you might guess, we're going to need to use the same trick that we just used. Because the exponential is continuous, we will integrate to get the expected value. So the expected value of e to the ty is the integral from 0 to infinity of e to the ty times 1 over beta times e to the negative y over beta dy. Here we're parameterizing this in terms of beta. Like before, we'll try to make this look like a PDF. So we will combine terms that look like the functional form of the PDF, pull constants that we're not going to need out of the integral. So we get 1 over beta times the integral of e raised to the negative y times the quantity 1 over beta minus t. we will manipulate this just a little bit to get the constants that we are looking for. So here we have 1 over beta minus t multiplied here to make this look like an exponential. That means we'll divide by 1 over beta minus t on the outside. Our integral now becomes 1 because it's just an exponential distribution. We'll combine terms in the denominator here with these multiplying constants. So we get 1 minus beta t raised to the negative 1 power for our exponential MGF, or 1 over 1 minus beta times t. So here is the probably more useful application of the moment generating function. We already know the expected value for most of our distributions. We already know the variance. We can use that variance to get the expected value of y squared. But here's why these are so very powerful. We can use moment generating functions to prove that a random variable follows a particular named distribution. Here's how we can prove that. Moment generating functions are unique. What this means is that if a distribution has a particular form of a moment generating function, no other distribution will have that same form. They will all have their own sort of functional form to them. So we'll let m sub x of t and m sub y of t denote moment generating functions of x and t respectively. If these moment generating functions are equal everywhere, then x and y actually follow the same distribution. So let's say that I have a random variable with moment generating function this. My moment generating function is e raised to the 3.2 times e to the t minus 1. What's the distribution of y? Well, we know 2 moment generating functions so far, so it's probably going to be one of these 2. This moment generating function here looks like the Poisson moment generating function, so we know that y must be Poisson. Now, most of the time you won't be given in real practice a moment generating function like this. What will happen is that you'll find the moment generating function of, say, a transformation or a linear combination and look for a functional form that matches. So that's where we're going with these functions. Incredibly powerful for finding distributions of particular transformations. So let's end this video just by providing a few moment generating functions that we'll need for both the discrete and continuous case. So for the binomial, the moment generating function is the quantity p times e to the t plus 1 minus p, all raised to the n. For the geometric, the moment generating function is PET over 1 minus the quantity 1 minus p times ET. The negative binomial moment generating function is then just the geometric moment generating function raised to the r. You have the Poisson one here as well. In terms of the continuous case, the moment generating function of the uniform is e raised to the tb minus e raised to the ta divided by t times quantity b minus a being the endpoints of the uniform. The normal MGF is one that we'll encounter frequently. This is e raised to the mu t plus t squared sigma squared over 2. The exponential moment generating function is one that we have already shown. The gamma, again, hearkening back to that exponential gamma relationship, has moment generating function 1 minus beta t raised to the negative alpha. There is no closed form solution for the beta moment generating function. So the beta moment generating function is not one that we'll be able to work with in this way. In the next video, we'll see some applications of moment generating functions, specifically toward finding transformations. See you then.